In this video, we're going to be looking at 3D unit vectors. Now, in an earlier video, we discussed two-dimensional unit vectors, and we said that a unit vector is any vector that has a length of 1 unit. So if we had a vector v, v is a unit vector if the length of v, the magnitude of v, is equal to 1 unit. And we said if that's the case, we could use the hat notation to say that v is a unit vector. V hat means v is a unit vector. We also saw how we could take any vector that isn't a unit vector and normalize it so that we convert it into a unit vector. That is to say, we take a vector whose length isn't equal to 1 and we normalize it so it has a length that is equal to 1. And we saw we could do that if we had a vector v. Well, then v hat, the unit vector version of v, so v, the same direction but a length of 1, is equal to our original vector divided by the length of our original vector. So v hat is equal to v divided by the magnitude of v. Now, interestingly, everything that I've just written here on the whiteboard still holds true for three-dimensional unit vectors. A 3D unit vector is no different than a 2D unit vector. It must have a length of 1. It's still noted using the small hat on the variable name. And to normalize a 3D vector, we use the exact same equation that we've used to normalize a 2D vector. So let's have a look at how we would normalize a 3D vector to generate a 3D unit vector and then make sure that the length of that unit vector is indeed a value of 1. So if I had some three-dimensional vector, let's say I had a vector A, and I'm just going to pick some random values. So I'm going to say its x is 3, its y is 1, and its z is 7. Well, we know we could find the length of this vector, the magnitude of this vector, and we could, in doing that, prove that this isn't a unit vector because its length is going to be greater than 1. So we saw how we could find the magnitude of a 3D vector. The magnitude of our vector A is going to be equal to the square root of x squared plus y squared plus z squared, which is going to be equal to the square root of 3 squared plus 1 squared plus 7 squared, which is going to be equal to the square root of 9 plus 1 plus 49, which is going to be equal to the square root of, well, 1 plus 49 is 50, plus 9 is going to be 59, so it's equal to the square root of 59. Now, I am going to round this into an approximate value just so that we can use numbers to keep this as simple as possible, and then I will go through and show how this does work using our absolute value, that is our accurate value rather than absolute, as that's another mathematical term, our accurate value that is the square root of 59. So this is the exact same procedure we took with the two-dimensional case. So the square root of 59 is 7.68 approximately, so 7.681. So approximately 7.681. That means the length of our 3D vector that travels 3 units in x, 1 unit in y, and 7 units in z, the length of that vector is approximately 7.681. Now we said to normalize a vector, we take a vector and we divide it by the magnitude of that vector. We divide it by the length of the vector. And what this meant in our 2D case is that we take each component of our vector and we divided that component by the length of our vector. It's the exact same thing here with the 3D case. If we want to normalize A so that we have a unit vector in the same direction as A, we're going to take each component of our 3D vector and we're going to divide it by the length of our vector A. So that means A hat is going to be equal to A divided by the magnitude of A, which is equal to A divided by 7.681, or I should say approximately equal to, since this is an approximate value, which is approximately equal to, so we had 3 as our x component. Well, we need to divide 3 by 7.681, we had 1 as our y component, so we divide 1 by 7.681. I will give myself some more space here. So let's extend our vector down a little bit further. There we go. And for our z component now, just as like in our 2D example where we have our components in x and y and we divide those by the length, with our z component 7 we simply divide that by the length as well. So 7 divided by 7.681. Fantastic. So if we actually work this out on a calculator, we're going to get a vector that has, in the x component, we need 3 divided by 7.681. So that's approximately 0.391. In the y component, we need 1 divided by 7.681. That's approximately 0.130. And for the z component, we need 7 divided by 7.681, which is approximately 0.911. Fantastic. So this is a hat. This is our unit vector in the direction of A. And what this means is that this vector should have a length of 1. So let's check that. We know the magnitude of A should be equal to a length of 1. Now we know, again, we saw this in our 2D case, because I have found an approximate value for the square root of 59, and then because I have found approximate values for each of these fractions, due to our rounding error, this isn't going to be exactly equal to 1. But it's going to be close enough. We can then go back through and actually take our square root and use that in the calculations and prove that actually this is exactly equal to a value of 1. So the length of our unit vector is going to be equal to the square root of x squared plus y squared plus z squared, which we know is equal to the square root of 0.391 squared plus 0.130 squared plus 0.911 squared. Fantastic. So that is going to be equal to the square root of, I'm going to use a calculator to work out this bit under the square root. So we have 0.391 squared plus 0.130 squared plus 0.911 squared is equal to 0.999, so very close to 1, which means our result is equal to 0.999, find the square root, 0.999, again, very, very close to 1, so 0.999. So this is very close to 1. The reason it isn't 1 is, again, because of these rounding errors that we have introduced both when we found the square root of 59 rather, and when we evaluated our fractions. So again, because of those rounding errors, that's why this isn't exactly equal to a value of 1. So just as we did with the 2D case, I'm now going to go back through, but use the square root of 59 to show this. So I'm going to bring up a new layer on our whiteboard, and we know that A is equal to 317. So A is equal to the vector 317. And we saw that the length of A was equal to the square root of 59. We'd already calculated that here. We saw the length of A is equal to the square root of 59. So we know to find the unit vector in the same direction as A, we need to normalize A, and that means we need to take A and divide it by the magnitude of A, which means we take A and we divide it by the square root of 59. We know what this means is we need to take each component of A and divide each component of A by the square root of 59. So it's going to be equal to the vector the first component of our result is going to be equal to the first component of A, 3, divided by the length, the square root of 59. So this is going to be equal to 3 over the square root of 59. The second component of our result is equal to the second component of A divided by the length, so divided by the square root of 59, so 1 divided by the square root of 59. And the final component of our results equal to the final component of A, which is 7, divided by the length, which is the square root of 59. So this is our unit vector. This is A hat. And it's got the x component 3 over root 59, the y component 1 over root 59, and the z component 7 over root 59. So if we then found the length of A hat, we can prove that this is very accurately a unit vector with a length of 1. So the length, the magnitude of A hat is equal to the square root of x squared, so 3 over root 59 squared, 59 squared plus y squared, so 1 over root 59 squared, plus z squared, so 7 over root 59 squared. Fantastic. So this is going to be equal to square root of, and again we saw this with the 2D case, this is equal to 3 squared over the root of 59 squared plus 1 squared over the root of 59 squared plus 7 squared over the root of 59 squared, which is equal to the square root of 3 squared is 9 over the square root of 59 then squared. Obviously these are going to cancel, so that's equal to 9 over 59 plus 1 squared is 1 over 59 plus 7 squared is 49 over 59. Because these are all the same denominator, we can combine these fractions together, so that's equal to 9 plus 1 is 10 plus 49 is 59 over 59. Obviously 59 divided by 59 is equal to 1, so it's equal to the square root of 1, and the square root of 1 is obviously equal to 1. So just as we did with the 2D case, we've shown by using the most accurate representation of our vector, we've shown that this is indeed a unit vector with a length of 1. So to recap, there is no difference between a unit vector in 2D and a unit vector in 3D. They both have a magnitude, a length of 1 unit, and they can both be generated by normalizing any vector by dividing that vector by the length, the magnitude of that vector. So there's really no difference between a unit vector in 2D and a unit vector in 3D. I'm going to set a couple of questions for you guys to work through on your own. And in these questions, because I'm making them up as I go along, there's no guarantee that the length of these vectors is going to be a nice round number. So if it is looking like you're going to have to take the square root of some number that's not a square number, then it's perfectly acceptable to leave the final vector using the square root form, so using the component of a vector divided by some square root. That's perfectly acceptable. In actual fact, it's more accurate than using a calculator and rounding up the values as we've just seen as we work through that example there. So question 1, we're going to have a vector. I'm going to say we have a vector b, and that vector is going to have 6 in x, minus 1 in y, and 2 in z. And I'd like you guys to find b hat. So I'd like you to find the unit vector that has the same direction as b, please. So go ahead and pause the video, give this an attempt. Once you have a solution, or if you get stuck, unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So we're going to be normalizing b. That means to calculate b hat, our unit vector in the same direction as b, we're going to take b and we're going to normalize it by dividing it by the magnitude of b. So the first thing I'd like to do is calculate the magnitude of b, which we know is equal to the square root of x squared plus y squared plus z squared. So 6 squared plus minus 1 squared plus 2 squared, which is equal to the square root of 36, plus minus 1 squared is positive 1, so plus 1, plus 2 squared is 4, so plus 4. This is equal to the square root of, well, 36 plus 4 is 40, plus 1, 41. Now this isn't a nice round number, so I'm going to leave this just written as the square root of 41. And now we need to divide b by our magnitude, by the square root of 41. So what that means is we're dividing each component by the square root of 41, and that's going to scale b down so that it has a length of 1. So b is equal to, I probably need quite a bit of space in the vertical direction here to fit all this in. So we're going to take our x component, which is 6, and divide that by the length, which is the square root of 41, giving our new x component equal to 6 over the square root of 41. We're going to take our y component, which is negative 1, divide that by the length, giving our new y component as negative 1 over 41. And finally, we're going to take our z component, which is positive 2. We're going to divide that by our length, which is the root of 41. And that's going to give us a z component of 2 over the root of 41. So the result you were looking for, and this is b hat, my apologies, not b, that's b hat. B hat, our unit vector in the direction of b, is equal to 6 over the root of 41 in x, minus 1 over the root of 41 in y, and 2 over the root of 41 in z. So that's question 1. I'm going to set another question here, and then we will conclude this video. So question 2, let's say we have a vector c, and this has minus 2 in x, 3 in y, and minus 4 in z, say. And I'd like you to find c hat. Again, just as in question 1, if this doesn't come to a nice length, because I've just made up these numbers off the top of my head, if this doesn't come to a nice length, then you can leave it written in square root form, and that will be absolutely fine. So go ahead and attempt to answer this question. Once you have a solution, or if you get stuck, unpause the video and I will work through the solution here on the whiteboard. Okay, welcome back everyone. So again, we're attempting to normalize vector c in order to get a unit vector that has the same direction as c. So to do that, we know that c hat is equal to c divided by the magnitude of c. So we need to work out the magnitude of c. We can do that using our equation from an earlier video, which we know that the magnitude of c is equal to x squared plus y squared plus z squared. So it's equal to minus 2 squared plus 3 squared plus minus 4 squared, which means it's equal to the square root of minus 2 squared is going to be 4, plus 3 squared is 9, plus minus 4 squared is 16. So that's going to be equal to 4 plus 9 is 13, plus 16 is 29. So the square root of 29, that's not a square number, so I'll leave that written as the square root of 29. So that means c hat is equal to c divided by the square root of 29. So we need to divide each component of c by the square root of 29. So our resultant vector, I will need probably quite a bit of space for this. There we go. Our resultant vector's x component is going to be the x component of c, minus 2, divided by our length, which is root 29, so minus 2 over the square root of 29. The y component of our unit vector is going to be the y component of c, which is 3, divided by our length, which is the square root of 29. And the z component of our unit vectors, the z component of c, minus 4, divided by our length, the root of 29. So minus 4 divided by the square root of 29. And this is the answer that you were looking for. So really, hopefully you've seen that there's nothing more to unit vectors in 3D than in 2D. In both 2D and 3D, unit vectors simply have a magnitude of 1. They are 1 unit long. And in both 2D and 3D, we can create a unit vector from any vector by normalizing it. It's the exact same process in both 2D and 3D. We take the vector and we divide it by the length of that vector, which means we take each component of the vector and we divide each component by the length of the vector. So that is going to conclude this video. Thanks a lot for watching, everyone.